What I want to do now is adapt the iterators we were already working on, our homemade iterator objects for the vectors of our int vector type, which we've already seen. We can create the iterator, we can walk it along, we can walk it forwards and backwards, we can access the element that it points to, but we can't yet run for each loops, and we can't yet run the usual iterator loop that we've seen. And that's because a couple of operations are still missing. So I will try compiling this and observe the compiler does indeed throw a tantrum about it. And our goal in this video is to add those last few operations. Strangely, you can see it is still complaining about begin. That's a case where the compiler is getting confused. It's actually the absence of .end that's confusing it. Okay, so I have this. I want to also make a couple of points later about these operations again, just to recap some of that stuff. In the meantime, here is my iterator class. It's basically the same as it was in the last video. I've made a couple of minor, I've touched up a little bit, but we have a constructor that when an iterator is created, we associate it with some particular instance of int vector, because that's where we're going to be getting the elements. It stores internally an index to keep track of where it is in the sequence. If I use the star operator, I basically just defer that to .at on the vector. When I use the plus plus and minus minus, that would be the prefix versions of those operators, I walk the iterator forwards and backwards. What I need now is the notion of the iterator becoming invalid. So we know already that if I move an iterator too far, it'll walk past the end of the array. And we understand that the usual abstraction presented by iterators is whenever an iterator points to an invalid position, it becomes equal to a special iterator value that's always returned by the member .end, which we're now going to have to write. So I'll just put that there as a placeholder. So what I want is for, if we go back down to main to look at our iterator loop, I would like to be able to iterate by starting at .begin and keep walking until the iterator is equal to v2.end, which will return some invalid iterator. This means I need two things. I need .end, obviously, but I need some way of comparing iterators together. And this is an operator. The not equal to operator is an operator, and I'm not allowed to use that unless it's defined for the type that I'm trying to use it on. And so I'll need to write not only a .end function and not only some logic to decide when an iterator is invalid, but also I'll need to write an operator to allow me to compare two iterators. That is the goal for this video. Okay, so I'm going to do that in a few stages. The first thing is I need to keep track of whether an iterator is currently valid. And the logic that I want to use is once an iterator becomes invalid, it should never be valid again. So here is a vector. And here is some possible iterator, some very strange portrait mode iterator. Let's try squaring that off. Here is some iterator I have over the vector. Suppose it points here. If I increment this iterator, then it'll point to a position that doesn't exist. And I would argue certainly if we're pointing past the end of the vector, the iterator should be considered invalid. An iterator that points past the end of a vector is always invalid. But there's, I guess, a different conceptual question, which is suppose I keep the iterator. So currently the iterator's internal index is index 4. I guess. Suppose later I add an element to the vector. Now the vector does have, that's index 3, not index 4. Now the vector does have 4 elements, and it does have an index 3. Should this iterator become valid again? I think the answer is no. As soon as the iterator is invalid, it is invalid forever. Doesn't matter what happens to the vector. The iterator should be invalid forever. So how do I manage that? Here is the way I'm going to do it. I could otherwise just use the index to decide if it's valid. I could say, look, if the index is bigger than the size of the vector, the iterator is invalid. I don't want to do that. I want to instead say, if I ever detect that the index has gone out of range, I'm going to set a special Boolean value to say that the iterator is now permanently invalid. So I'm going to call it isValid. This is just a flag, true or false. If this ever gets set to true, or ever gets set to false, then this iterator is going to be invalid forever. And trying to use an invalid iterator is invalid, obviously. Okay, so now I'm going to modify my constructors to adapt to that. So when you create a valid iterator, I'm going to assume isValid is true. But I will, in my constructor, do a quick check. I'll say if the index is greater than or equal to the size of the vector, then I guess isValid is false. Okay, so I'll actually do that as an extra check, just in case whoever called the constructor didn't know what they were doing. Again here, because indices are unsigned ints, there's no way an index can ever actually be negative. So there's no reason I need to check that the index is greater than or equal to 0, because it has to be. But if the index is ever greater than or equal to the size, it's not a valid index, then the iterator is permanently invalid. And then same thing here. So if I try and do a plus plus operation, okay, well, if the iterator is already invalid, so if is valid is false, so this notation, recall, is saying if not is valid. In other words, if is valid is set to false, well, then I'm done. I don't bother incrementing an iterator that's not valid. So I just return star. I just quit immediately. Otherwise, I do modify my index. Now, if this modification resulted in the index being greater than or equal to the size of the vector, now the iterator is invalid. Okay, so I perform the modification. If the result of the modification makes the iterator invalid, then I set it to be invalid. And I do something similar. I'm actually going to steal the same notation here. I do something similar here. If the iterator is already invalid, just do nothing. Otherwise, do the decrement. And I know this seems a bit bizarre. Why would I do this check? The index is not getting any bigger as a result of line 107. The issue is because the index is an unsigned int, if the index is equal to 0, then decrementing it could result in something weird happening. And so maybe actually, now that I think about it, in the middle of the video, I'm going to change my strategy. I'm going to say, you know what? If you try and decrement and the index is 0, you can't do it. Sorry. So if the index is equal to 0, I'm not letting you move the iterator any earlier. Instead, decrementing an iterator to be before the sequence obviously makes the iterator invalid. Otherwise, the iterator is going to be valid when we're done. If the index is at least 1, I am allowed to decrement the index. So I'll do this. Okay, so my minus minus operator is a little bit different now. It would have been the same with what I already had, but I feel like this is maybe more readable. So if the iterator is not valid, leave it invalid and do nothing. If the index is 0, then set it to be invalid and otherwise do nothing. And then otherwise decrement the index as usual. And then down here, I guess I should build in a bit of protection. I should say, look, if the iterator isn't valid, do not try and access the element, please. So I'll throw an exception, std. Maybe we'll throw out of range there. There we go. Maybe we'll say dereferencing an invalid iterator, because that makes no sense. All right, because nobody should ever try and use an invalid iterator, we should build in some proactive error checking to make sure that they don't. Interestingly, in most cases, this would still throw an exception, but it's good to catch that and just get out front of the problem. Okay, so I now have operations to allow an iterator to be either valid or invalid. I'm going to add one other thing, which is a second constructor. I'm going to add a constructor that doesn't take an index. It takes only one argument, and that is the associated vector. And the goal of this constructor is to construct a deliberately invalid iterator, because we know that we do want that idea of the special .end iterator that is never valid. So we'll initialize index to 0 for lack of any better ideas, and we'll initialize is valid to false. So if I call the constructor that only takes one argument, I'm saying give me a deliberately invalid iterator. All right, I now have almost everything I need. Let's actually see how the compiler is doing with this. Okay, so the compiler is now saying, if we look at, there's where we compile, it's complaining on line 133 that my .end function isn't ready yet. I think we can write that. So I'm going to create an iterator called result, positioned with the current vector but invalid. Recall that I just wrote that one argument constructor. If I call the constructor that takes one argument, then it will construct an invalid iterator. I still want it to be associated to this particular vector, because maybe that'll come in handy in a minute. Okay, so in this case, if you call .end, it will now return a value. So the compiler was complaining about that. Let's see what else I have to do. There are only two errors, and they're on lines 193 and 200. So 193 is this for each loop, which, as I've said, 193 is actually just really, the compiler expands it to this. So we shouldn't be too surprised that it gives the same error for both loops. On line 193, it's more cryptic because it doesn't want to show you, it doesn't want to really admit that it's expanding it out, but it is. On line 200, it says, okay, I'm good with this. v2.begin sounds good. Plus plus iter has never been a problem, but this is difficult. It's no longer complaining that .end doesn't exist because I've added .end, and it's saying, okay, hi, so you're trying to use the not equal to operator not equal to, on an iterator and an iterator. So you can see, it can tell both operands are iterators. The problem is there is no operator not equal to for iterators. So you have to define one. Unlike the single equals sign, unlike assignment, the compiler does not attempt to make you operators for things like this. If you want to compare two objects, you have to tell it what to do. There are ways, theoretically at least, in C++20 to ask the compiler explicitly to try and make you an operator for free, but it doesn't give you one for free unless you ask for one or create one yourself. I'm going to show how we create one ourselves, because comparing two iterators is a little bit more complicated than it would seem. So what I want to do is say two iterators are equal in the following cases. If one of the two iterators is invalid and the other one is valid, then they're always not equal. So a valid iterator and an invalid iterator are never equal. On the other hand, two invalid iterators, regardless of what else they have inside them, two invalid iterators are always equal. So any invalid iterator is always going to be considered equal to any other invalid iterator. That ensures that no matter how this iterator became invalid, it will always compare as being equal to this other .end iterator that's also invalid. And then finally, if both iterators are valid, then they're only considered equal if they refer to the same index. Now, one other thing we would otherwise, in a different setting, be concerned about is we don't want two iterators to compare as equal if they refer to different vectors. But because we don't generally find ourselves in cases where we have two iterators over different vectors that we're comparing, we're not going to worry about that for this video. We're going to adopt that simplification. So what I want is a not equal to operator. Now, as of C++20, which as you've noticed we are using, as of C++20, if you want a not equal to operator, all you have to do is define the equals operator. If you define an equals equals comparison operator, the compiler defines the not equal to operator for you, because that's just the opposite of equals equals. You are welcome to define both yourself, but the current idiom in C++ is always to define the equals equals operator only, and the compiler will generate for you a not equals operator based on the equals operator. So I'm going to do that. So here is operator equals equals. And we know this is being declared as being a member of the iterator class, which means the left-hand operand will be the current iterator, and the right-hand operand will be something we take as an argument. So iterator const reference, actually I'll just do iterator reference for now. We're not worrying about constant iterators for this video. Well, this is the other iterator. Okay, so what does it mean for two iterators to be equal? Okay, I'm going to break down the three cases I just listed. If both iterators are invalid, then they are always equal. If only one is invalid, then they are always not equal. So a valid iterator is never equal to an invalid iterator. If both are valid, they are equal if and only if they have the same index. Okay, there are my three cases. I'm just going to write those as three if statements. So if this iterator is not valid, so if it's invalid, and the other iterator is also not valid, then they are always going to be equal by the logic in the comment. Okay, so in that case, the equals operator returns true. And hopefully you can see writing the equals operator is sort of nice because the not equals operator requires thinking about things as double negatives, which is sort of annoying. So okay, if both are invalid, then they are equal. They're always equal. Any two invalid iterators, because they're going to be invalid permanently, they're always considered to be equal. If only one is invalid, so at this point on line 128, we know that they are not both invalid. So if I discover that only one of them is, so if either of the two is valid, so if is invalid, so if either this one is invalid or the other one is invalid, then we've got a problem. Then they are definitely not equal. There's no way that a valid iterator will ever equal an invalid one. Okay, so there are the two cases. If both are invalid, then we return that they're equal. If only one is invalid, keeping in mind that this is an inclusive OR, but the case where they're both invalid has already been handled. If one of them is invalid, then they are not equal. And then finally, down here, we can assume they are both valid. So I just return, maybe I'll use an if statement to make it more clear. I'll return if the index of this one is equal to the index of the other one, then they are equal. So return true, and then otherwise return false. And there I have it. I have now written the equals operator for my iterator, and we'll try compiling and see if it complains. And it works. Notice that although I'm using the not equal operator when I use the iterator, if I provide the comparison equals operator, the compiler understands. And it will define a not equal operator to just be the opposite of the equal operator. So it just calls the equal operator and then flips the result from true to false. So if they are, if I compare x and y, so just to be clear about this, x is not equal to y if x equals y returns false. So obviously, if I have the equals comparison, then it's pretty easy to come up with the not equals comparison. And the compiler, as of C++20, will do that for you. It used to be, so even in 2021 when I taught this course, you would have to define both yourself. Usually what you would do is define the equals operator and then make the not equals operator just call the equals operator. But you have lots of options. Fortunately, in C++20, the compiler can do the not equals operator for you. So the code compiled, and that means I should try running it. Okay, so here is where we try printing with a for each loop. And we'll notice that it does print the vector. I am actually able to print one of my own vectors with a for each loop. Because I provided the functionality for iterators, the compiler can now convert a for each loop to something that can run on my vector. And if I, for some reason, was the type to prefer iterators, I have that option too. And we can verify that these are indeed the vectors I'm supposed to be printing. So the first vector v1 never got modified. That's the result at the end of the code. We saw in the previous video that v2, once all the modifications are done, is in fact this. And so I'm now able to use iterators to iterate over and modify elements of my vector. And now, in every way except the angle brackets, this int vector object is, I think, pretty much interchangeable for std vector for all of the uses we had for vectors of ints early in the course. Now, it remains to be seen exactly what those angle brackets are and how we could make a vector that works with literally anything. We will actually have that concept by the end of the week as well.